This video lecture briefly demonstrates the use of equivalence rules and inference rules. Let's start with the definition of a valid argument. A propositional width is a valid of the form that is shown here, is a valid argument when it is a tautology. So the format that we're talking about is a conjunction of propositions. So we, for example, have here P1 is a proposition, P2 is a proposition, P3 and to N, and we have a conjunction here. So these logical ends, that is also called a conjunction. And we call these propositions here P1 to Pn, we also call them hypotheses. And Q, that's the right-hand side of our implication, is the conclusion. So let's look at a particular example here. Let's look at the expression or the statement, if George Washington was the first president of the United States, then John Adams was the first vice president. George Washington was the first president of the United States, therefore John Adams was the first vice president. So in these three sentences, we have a couple of pieces of information. We have a couple of statements. So, for example, we have the statement that George Washington was the first president, or that's the statement, first president of the United States. Then John Adams was the first vice president. That's a statement. And then we have a couple of other things in here. So let's say that the statement George Washington was the first president of the United States, we call this proposition A. And then secondly, John Adams was the first vice president, we call this proposition B. So we have A, George Washington was the first president, and B, John Adams was the first vice president. So what the first sentence says is actually not that George Washington was the first president, but it says if George Washington was the first president, then John Adams was the first vice president. So the first sentence actually says A implies B. If A, then B. The second sentence, though, says George Washington was the first president of the United States. This is a proposition, a fact, that says A is true. George Washington was. That's the statement of the second sentence. So, therefore, John Adams was the first president. This is how the argument follows. So what we have here is actually A implies B, that's the first sentence. Then we have A, that's the second sentence. The last sentence says therefore, which means it implies B. So this is actually the format of a valid argument. We have a valid argument, we have a sequence of propositions, P1, connected by a logical end, it's also called a conjunction, P2, and an implication that implies our conclusion, Q. So if this here is always true, then this is a valid argument. And so what is left after we basically take the verbal argument here, we define our propositions and we translate this verbal argument into a logical structure. In this case, these three sentences basically can be written as A implies B and A implies B. So again, this is the first part, our hypothesis, and the second part is the implication. There are a couple of ways we can prove that this is true. For once, we could create a truth table and just write those down, and if for any value of A and B, this width is always true, then we have proved that this is a valid argument. Alternatively, in particular if the arguments get much longer than this, we might actually try to use some derivative rules. So we might try to define rules that allow us to translate the width into a different format, so that at the end we have a simplification that shows that our hypothesis is, our conclusion is true. So here we have a number of equivalence rules, and how this is can be read is, if we find an expression P or Q, then we can easily also write this as Q or P. So this is called the commutative law, and we use for later examples, according to the textbook, we use some abbreviation to have these rules, indicate these rules. So for example, P or Q is equivalent to Q and P. That means one can be written as the other one. This also applies to the logical AND. So P and Q is equivalent to Q and P. It might not apply to other types of operators. Another fairly straightforward is the rule is the associative rule, which says that if we have something like this, of the form like this, P or Q in parentheses or R, we can actually move the parentheses. So if we have P or Q, we have the parentheses around here, or R, we can also move the parentheses to this part. There is basically no preference. The same is also true for the logical AND. The De Morgan's law is a little bit more interesting, and that law describes when we have P or Q negated. If we want to break the parentheses, so we want to bring the negation here inside the parentheses, what happens is that this basically flips the operator. So a logical OR becomes a logical AND. And conversely, a logical AND becomes a logical OR. The De Morgan law is quite useful, but it's kind of tricky, because when we bring the negation into the parentheses, then we switch the logical operator. Implication law, the rule, so an implication can also be written as not P or Q, and sometimes that can be helpful to kind of reformat implications, or if we have a expression like this, we might be able to write it as a implication. The double negation, very useful. And finally, this is actually the definition of the equivalence rule. So two widths, or two expressions, P and Q, are equivalent if P implies Q and Q implies P. So the equivalence means that if two expressions are equivalent, P implies Q, then one can substitute the other one. Inference rules are similar to equivalence rules, but here we actually, if we find a particular width, or actually several, usually two pieces, we can add another one. So for example, if we find a proposition P and we find a proposition P implies Q, we can add the proposition Q. This is actually one of the most popular inference rules. It's called the monosponence. That means if we have a proposition that is P implies Q, what that means is, so that's like a rule. If we say P implies Q and we know that P is true, then we can infer that this Q is also true. P implies Q is one part, that's one hypothesis. The second one, we use the comma in the inference rule, but what we really mean is that also P is true, and that implies Q. So If we have this format here, then and this is also true. So if this is what we write here is true, we have a tautology, then this becomes an inference rule. Pretty much all the inference rules that we see here can be written like this, and then we need to show that they're always true, that they're always a tautology, and then we have an inference rule. Whatever tautology you can come up with, how complicated it is, if you can write it into a format P1 and P2, whereby P1 and P2 can be actually widths of any complexity, and you show this is a tautology, then you can basically produce your own inference rule and say we have P1, comma, P2, and this allows us to derive Q. Let's look at another argument here. If interest rates drop, the housing market will improve. Either the federal discount rate will drop or the housing market will not improve. Interest rates will drop, therefore the federal discount rate will drop. If we have a verbal argument like this, we want to identify our propositions. One of the propositions is that interest rates drop. So let's say we call this I, as our interest rate. Another proposition is that the housing market will improve. Let's call this H. And then we have the last one is that the federal discount rate will drop. This is this one here, the federal discount rate. We just call this, so that's this part, discount rate will drop. We call this F. So I stands for house interest drops. H stands for the housing market will improve, and F stands for discount rate will drop. Let's look at how we can translate this verbal argument into a formal logic expression. The first sentence says, if the interest rate drops, then the housing market will improve. So this is an implication, if then. So we have I implies H. The second sentence says, either the federal discount rate will drop or the housing market will not improve. So we have a negation here. So we have either or, here's the or. So let's say this becomes F or, and then not housing market will not improve. That is a not H. The last sentence, the next sentence says interest rates will drop. So somebody's making the statement I. And then, therefore, the federal discount rate will drop. That is F. So what we haven't included in here yet is the connectives. We have the first sentence, that's a hypothesis, I implies H. The second sentence says either the federal rate will drop or the housing market will not improve, that's F or not H. And the third sentence says interest will drop. So these are actually all hypotheses, and we imply that there's a logical and. And then the argument comes to the conclusion that this will imply F. So what we have here is an expression of this format, and we want to find out, is this a valid argument? And in order to do that, we need to take this expression here and see if this is basically a tautology, so it's always true. Or alternatively, we could also just see if we take this portion here and see if we can transform it with inference rules to come to the conclusion F.